high-yield overview of the core foundational concepts of coordination chemistry specifically tailored for UPSC-IAS Mains Chemistry Optional, Paper I. Coordination chemistry carries significant weight in inorganic chemistry for Paper I questions consistently test deep conceptual understanding, structural derivations, spectral interpretations, and thermodynamic versus kinetic aspects. 1. Fundamentals and bonding theories. Coordination chemistry centers on complexes formed between central transition metal ions, Lewis acids, and surrounding ligands, Lewis bases, via coordinate covalent bonds. A. Werner's theory. Primary valence, ionizable, non-directional, corresponds to the oxidation state of the metal center. Secondary valence, non-ionizable, directional in space, corresponds to the coordination number, Cn. B. Crystal field theory, CFT. CFT treats metal-ligand interactions as purely electrostatic, point charges, dipoles, and explains d-orbital splitting under different geometries. Octahedral, O_H, splitting. Degenerate d orbitals split into two sets. Lower energy T_2 grams, D_XY, D_YZ, D_ZX, and higher energy E_G, D_Z squared, D_X squared Y squared. Total crystal field splitting energy is denoted as delta_O, or 10, dq. CFSE calculation, where P is the pairing energy and M is the number of extra pairs formed. Tetrahedral, T_D, splitting. Orbitals split into lower energy E, D_Z squared, D_X squared Y squared, and higher energy T_2, D_XY, D_YZ, D_ZX. Splitting parameter, delta_T equals frac 4, 9. Delta_O. Because delta_T less than P in almost all cases, tetrahedral complexes are almost exclusively high spin. Square planar, D_4H. Splitting, derived by extreme tetragonal elongation, along the z-axis, of an O_H field. Orbital energy sequence, D_XZ, D_YZ, less than D_Z squared, less than D_XY, less than D_X squared Y squared. Predominant in D8 metal ions with strong field ligands, e.g., PT2, PD2, Ni2, with Cn-, C-Jan-Teller distortion, JTD, theorem. Any nonlinear degenerate electronic state will undergo structural distortion to lower its symmetry and remove degeneracy. Key observations in O_H, strong JTD, unequal occupation of E_G orbitals, e.g., high spin D4, low spin D7, D9 such as Cu2. Results in significant tetragonal elongation, Z-out, or compression, Z-in. Weak JTD, unequal occupation of T_2 grams, orbitals, e.g., D1, D squared, high spin D6. D ligand field theory, LFT, and molecular orbital, MO, theory. Addresses CFT's limitation of ignoring covalent metal-ligand interaction. Sigma bonding, overlap of metal E_G, A_1G, T_1U, orbitals with ligand donor orbitals. Pi bonding, pi donor ligands, e.g., I-, Cl-, donate electron density into vacant metal T_2 grams, orbitals, Right-arrow decreases, delta_O. Pi acceptor ligands, e.g., Colorado, Cn-, NO+, accept electron density from filled metal T_2 grams, orbitals via pi backbonding, right-arrow increases, delta_O, spectrochemical series placement. 2. Magnetism and electronic spectra. A. Magnetic properties. Spin-only magnetic moment, μ_S_O, where n is the number of unpaired electrons. Orbital contribution, quenched in first-row transition metals by crystal fields, but retained when T_2 grams, set is unsymmetrically filled, e.g., T_2 grams, 4 E_G 0. B. Electronic spectra and selection rules. Laporte selection rule, delta L equals PM1. D. Text, D transitions, delta L equals O, are Laporte forbidden in centrosymmetric complexes, O_H, but gain intensity via vibronic coupling, mixing of P and D vibrational modes, or non-centrosymmetric geometry, T_D. Spin selection rule, delta S equals 0. Transitions between states of different spin multiplicities are forbidden. Charge transfer, CT, spectra, high-intensity transitions. LMCT, ligand to metal, observed in high oxidation state metal centers with oxidizable ligands, e.g., MNO_4 CR_20_7 2. MLCT, metal to ligand, observed in low oxidation state metals with low-lying pi orbitals on ligands, e.g., Fe, Bipi, 3 2+. 3. Stability and reaction mechanisms. A. Thermodynamic versus kinetic stability. Thermodynamic stability, quantified by stepwise kappa_n, and overall beta_n formation constants. Factors affecting stability: metal ion charge, size ratio, Q, R. Irving-Williams series for divalent 3D ions, Mn, 2, less than Fe, 2, less than company, 2, less than Ni, 2, less than Cu, 2, greater than Zn, 2. Chelate effect, increased thermodynamic stability due to positive entropy change, delta S circ greater than O. Macrocyclic effect, enhanced stability due to both favorable enthalpic and entropic contributions. B. Reaction mechanisms in octahedral complexes. Substitution reactions, dissociative, D or I_D, loss of leaving group forms a 5-coordinate intermediate, trigonal bipyramidal or square pyramidal. Associative, A or I_A, attack of incoming ligand forms a 7-coordinate intermediate. Trans effect, in square planar complexes, influence of a non-leaving ligand, T, on the rate of substitution of the ligand trans to it. Transdirecting order, I less than CL less than NH_3 less than H_2O versus CN approximately CO, approximately C_2H_4 greater than PR_3 greater than NO_2 driven by sigma inductive effects, ground state weakening, and pi acceptor ability, transition state stabilization. C. Electron transfer reactions. Inner sphere mechanism, requires a bridging ligand, e.g., Cl N_3 between both metal centers to facilitate electron transfer. Outer sphere mechanism, no ligand bridge formed, electron tunnels through space between intact coordination shells, explained by Marcus theory. 4. High-yield focus areas for IAS mains. When preparing answers for GS paper IV versus chemistry optional, always draw explicit orbital splitting diagrams, O_H, T_D, D, 4H, and clear Mo energy level diagrams when explaining spectra or bonding. Quantify CFSE in step-by-step detail rather than giving just the net result. Correlate structural distortions, JTD, directly with magnetic anomalies or electronic absorption band splitting.